We'll now look at related non-homogeneous systems. What we mean by this is if we look at these two systems here, the one on the left is non-homogeneous, whereas the one on the right is. However, they have the same coefficient matrix. So this is what we call related non-homogeneous and homogeneous systems. So we're going to do an example by solving these and seeing what the solutions look like and seeing if we can make any conclusions. So here's our augmented matrix. And when we're solving multiple systems that have the same coefficient matrix, we often do this where we put on several augmented columns. That way we don't have to solve the coefficient matrix more than once. We can do it all in one step. So we already have a 1 in the first row, first column. So we'll leave the first row alone for now. And so the next step would be to get zeros underneath that 1. The first one is a 3. So we'll do -3 row 1 plus row 2. That would be -3 plus 3 is 0. 3 minus 2 is 1. 12 minus 9 is 3. And then -3 plus 4 is 1. 0 plus 0 is 0. For the third row, it's a 2. So we'll do -2 row 1 plus row 3. -2 plus 2 is 0. 2 plus 0 is 2. 8 minus 2 is 6. We then have -2 plus 4, which is 2, and 0 plus 0, which is 0. Now that we've done that, we want to look at the second column. There's already a 1 in the second row, second column, so we can get zeros above and below that. This means our second row will stay the same for now, which was 0, 1, 3, and then a 1 and a 0. For the first row, it's currently a -1, so we'll add row 2 plus row 1. That would give me 0 plus 1 is 1, 1 minus 1 is 0, 3 minus 4 is -1, and 1 plus 1 is 2, and then 0 plus 0 is 0. For the third row, I'm going to multiply by -2. -2 row 2 plus row 3. That would be 0 plus 0 is 0. -2 plus 2 is 0. -6 plus 6 is 0. -2 plus 2 is 0. And then 0 plus 0. So this is now in the proper form, and we can see that we do have infinite solutions. For my non-homogeneous system, I have x1 minus x3 is equal to 2, and I have x2 plus 3x3 equal to 1. So when I solve this, x1 will be equal to x3 plus 2, x2 will be equal to -x3 plus 1, and then x3 is free. If I look at my homogeneous system, I have x1 minus x3 is 0, and x2 plus 3x3 equal to 0. This gives me x1 is equal to x3, and x2 is equal to -3x3, and x3 is free. So you can see that these are kind of related. If I look at my non-homogeneous system, it has this extra plus 2 and plus 1 that's not over here on the homogeneous system. But other than that, they are the same. And this is how they're related. Geometrically, whenever we graph this system on the right, this homogeneous system, it'll correspond to a line passing through the origin. If we graph the one on the left, the non-homogeneous system, it will be a line parallel to the homogeneous solution. However, it will no longer pass through the origin. So that's the main difference here, is it's basically kind of taking our graph and shifting it over. The other thing I will point out is every time we've solved a homogeneous system so far, you'll notice that the augmented column has been all zeros, and throughout the solving process, it has never changed. It's always been zeros. As a result, usually when we solve homogeneous systems, we leave off the augmented column and just solve the coefficient matrix, since that last column will always be zeros. As a result of this, we're going to look at this theorem. So the first part does depend on the linear system being consistent. So we know that there's a solution. In that case, our system is of this form H plus P, and these little arrows above it means we're dealing with vectors. These are going to be solutions throughout the whole system. It's not individual numbers. So what is H and P? H is our solution to our homogeneous system. If we solved a related homogeneous system, H would be the solution to that. And then P is a particular solution. What this means is if we take our non-homogeneous system and we look at the particular solution where our free variable is 0, then that corresponds to P, that solution. So it's a single particular solution of the system. So they will always have this form, the solution of the homogeneous system plus this particular solution when the free variable is 0.